Kia ora tātou, it's Bill here. I want to have a look in detail at this simple little program we've got, which is flashing LED. Now in Atmel Studio, I've got that open on the left-hand side. You can see I've highlighted this loop here, while one loop, and I want to look at this in a bit of detail and explain to you what's going on. Now, if I have a look at this, I've written it down. What a while loop does is whatever's inside the brackets, if this is true, then it will continue to repeat the operations inside these curly braces until this is false. Now, in this case, while one is always true, so it will never stop doing this. It will continue to do it forever. Now, let's have a look at each instruction. Set red LED, when this is translated into assembly language and then turned into machine code and put inside our microcontroller, this is a single operation and it will take about 1/16 millionth of a second to carry out, which is in fact 62.5 nanoseconds. Again, down here, the clearing of the LED, turning off the pin, that's again about 1/16 millionth of a second, 62.5 nanoseconds. This operation here, however, is a function call, and we're passing 1,000 to it because we want it to do something for 1 second or 1,000 milliseconds. So this function here is actually doing something, and it's just in a way slowing down our process of our microcontroller so that we can see the LEDs turn on and turn off. So what's it actually doing for 1,000 milliseconds? I'll have a look at a simple little function, and this is not quite what it translates into, but this one will show us the effect. So I'm passing this sum number, 1,000, and I'm multiplying it by 4,000 so that I get n equals 4 million. And then what I'm doing is, while n is greater than 0, subtract 1. Now, this will take a little while to do. And in fact, the amount of time that this takes to do is about 4/16 millionths of a second. So if we have this takes 4/16 millionths of a second and we're doing it 4 million times, then what we've done is we've delayed our microcontroller for 1 second. So our microcontroller is always actually doing something. It's never actually stopped waiting, doing nothing. It's always doing something. And we call this blocking, because this code blocks our microcontroller from doing anything else. This loop will continue to decrease by 1 and check to see if it's 0, and that will do that for a full 1 second, which means that during that time our microcontroller can do nothing else, and that's what we refer to as blocking. So if I go back to my main loop, what I've got here is I've got something that takes 1/16 millionth of a second. I've got something here which takes 16 over 16 or 1 second, and then I've got another 1/16 millionth of a second, then I've got another 1 second delay, and then it repeats again. So the crucial thing to remember is that these functions here, they are always actually doing something. This is the dynamic nature of a computer program. And it's something that's a little bit hard to grasp sometimes, and I get this sort of thing with some students when they're first introduced to this. They'll do things like they might miss out this line here and not realize what's actually going on and see the problem. If I left out this line, then the LED would turn on, it would wait for 1 second, and then it would turn off and immediately jump back to the beginning and turn back on again. So the LED would always appear to be on. If we took out both of these delays and we only had an LED turning on and an LED turning off, then the LED would be flashing, but of course it would be flashing at such a rate that we cannot see it. Our eyes cannot perceive that amount of flashing. And the LED, because it's on for half the time and off for half the time, almost, it's actually on for 1 cycle, off for 1 cycle, and then the jump back takes another cycle. So it's actually only on for 1 and 3 cycles. So the LED would appear dim. So the key thing to remember is that the computer, the microcontroller, is always doing something. So here it does this loop, then it spins its wheels here for a long time, doing this blocking thing, and then it comes here and does one operation, then it comes here and spins its wheels for 4 million times until it's delayed for a second, and then it jumps back to the beginning. So this is the dynamic nature of programs. The microcontroller does not stop at this point. It actually is doing something. And so the microcontroller is always doing something. We just have to tell it to stop. And that's why we would not normally use a delay like this in a program, of a real program, because then the microcontroller would be blocked and not able to do anything else. So there's a little bit of an explanation. I hope it makes sense to you. Cheers.